right, here we go. Here's a lovely experiment looking at the percentage efficiency of a ball bouncing. I've done this in lessons. Okay, I didn't realize it was going to be one that might come up. It was always interesting when they try and do something new. Let's have a look at this question. Okay, so we've got a ball being dropped from an initial height of 10 centimeters, and basically what you're doing is measuring the height before and after. Okay, so nice and simple. They repeat the procedure for the initial heights, and we've got 10.0, 20, etc., etc., etc. Okay, and what we're going to do is make some measurements for that. Now I think I've actually managed to scan this the wrong way. There we go. All right. So first thing we're doing there is measuring the maximum height. Now, okay, this seems to come up quite a lot. CIE likes to specify what height you've got to measure. In this case, it's the height of the bottom of the ball. Okay, so you're being asked firstly to calculate, measure it, sorry, to the nearest 0.5 centimeters. Okay, so what you're going to do is you're going to measure the bottom of the ball, and what I found is that went somewhere there. Very good. We've got 25, 26. We're going halfway through 25.5 centimeters. Okay, so that's all you have to do there. You're just measuring it to the nearest 0.5. Now, if you had, I don't know, 25.4, 25.3, you would measure it again to the nearest 0.5. This is just something that they're specifying. Whether it's correct scientific practice or not, we could debate for a while. We just want to get through this paper, so we're making sure that we're just following the instructions. Okay. You're then asked to calculate the percentage efficiency. Okay. We know the initial height was 30, final height is 25.5. We're going to do 25.5 divided by 30, which comes up as 85%. So far, so good. I think this is two things, and obviously I think you've seen before, I put it in the table. Now, this is where it gets interesting. All right. Again, every now and again, and to be honest, it makes it a bit more interesting, CIE changes up the format. Here's a change in format because firstly, we've got a really, really tiny bit of graph paper. I've never seen this before. All right, genuinely, don't know where this come from. Generally, what you are asked to do is to scale your axes so that you are making sure that you're putting your data on the right spots and that you're making it easy to read, etc., and using over half the graph. You don't really have much choice here because you've got such a small bit of graph paper. Key difference here is it tells you not to start the vertical axis from zero. Now, this is something that students do have trouble with. We think that we always have to start with zero, where you always have to go from zero to, maybe it would be 0 to 40 to 80 to 120 in this case. Yeah, you don't have to. You are being told not to, so you should not do that. So what I've done here is start at 70 because the numbers in the table don't go lower than 70. Okay, 70, 80, 80 to 90, and then 90 to 100. This means I'm using this really nicely. Okay, so as ever, I've not written on here, I should have really written that there. You're getting a mark here for doing a few things. One, writing your labels, percentage efficiency, no units, initial height in centimeters, that's one. Okay. Another one is for effective scaling, yeah, 70, 80, 90, 100, and then in the tens on this bit. And the last bit is the points. I've said this a few times, it is part of the marker's job, so that's my job, not necessarily for you guys, to look at your numbers and say, have they put these crosses on the right points? If they put them on the right points, then you get the mark. If any of the crosses is unclear, if it's not a nice cross, if it's, again, that technical term, a blob, then you do not get that mark. So just make sure your crosses are lovely drawn. You can run with a ruler, whatever you want. It's much easier to read. So that's the 3 marks. Again, I think these things used to be a 4-mark question. They split out into 3 and 1. The last mark is for drawing a curve of best fit. Now I'm going to be honest, I don't like my curve of best fit. All right, it's a bit bumpy. I don't like what I've done here, so I'm wondering if I'm on the borderline of whether that's a good one. I don't think I'd get that mark. Try and draw it as smooth as possible, only one line, and in that sort of smooth motion with your hand. Okay, if you have trouble with it, rub it out and do it again, which is what I've not done here, which I should have done. Okay, so we've done our graph. Okay, another classic question. We're being told that we're worried about this thing being vertical. Okay, how do we ensure it's vertical? Well, one way of doing it is to use what we call a set square. You put the set square next to the ruler and it should form a 90 degrees angle, and if it's forming a 90 degrees angle, then it is going to be a vertical one. If it is not forming a 90 degrees angle, it is not vertical. You could also use a protractor for this. However, we tend to use a set square because we guarantee that 90 degrees straight off. Okay, some more source of error. I've gone for 2 here just for fun. Why not? The first one was air resistance and the second one was parallax. I thought there could be some air resistance in the readings, which would cause some random variation. Well, what we do with that, we take multiple data sets, repeat them, and calculate averages. Notice in the question they've not talked about calculating any averages. Okay, so what I would suggest you do there is, make a suggestion, which is to calculate averages from repeat readings. Parallax is the idea of measuring your values using your eye from a different angle. It's always a good one when you're talking about falling things. Okay, now I thought about this. A really good way of doing it would be to set up a video, right? Watch it back frame by frame, so that you can ensure that you're getting the right values of your measurements. Okay, so you're not having to follow the ball, you're not having to view from a certain angle, you just view from a camera. Okay, last one. The ball is dropped from an initial height of 20, and bounces to a height of 16 with an efficiency of 80, and then falls and bounces again. I like this one. Okay, suggest how the value of percentage efficiency for the second bounce compares to the first bounce. Now, let's have a look here. We're starting with a height of 20 and we're getting 80%. We're then going to bounce from a height of 16, so essentially our new bounce, our next bounce is going to start with 16. So what's happened is the initial height has gone. We can imagine this is 2 bounces with different initial heights. Our initial height is decreasing. Okay, what's our percentage efficiency? Well, if you look back at your graph, which is somewhere around here, if you have a lower height, you tend to get a lower efficiencies from this graph. Okay, so this is where you're actually using the graph, all right, to have a look at what that value could be. We're going from an initial height of 20 to a new initial height of 16. You can see that the efficiency is dropping. Okay, so from our data, skip that one. Sorry. We expect a lower efficiency because the lower height appears to have a lower efficiency as shown in the table and also in the graph. That's a nice question, using the data and asking you to refer back to it and then relate your readings to there.